Hello, my name is Kyung. I'm happy to present our work about BIGexplore, Bayesian Information Gain Framework for Information Exploration. This is a joint work with Kyungmin Kim and Hyun, and it was done at Hyun University. In the early phase of design, designers focus on acquiring the various design informations to gain inspiration or develop their designs. Various alternatives were explored in this process, and the designer's searching goals also frequently changed. Thus, to support this process, an information system needs to understand the user's needs in real time to provide information accordingly. Recently, Bayesian information gain framework has garnered significant interest as an interaction method. This framework iteratively interacts with the user by updating the probability value of target based on the current user action and by providing a next view accordingly. However, the BIG framework has two main limitations. First, the provided next view is not sequential from the user's perspective because the BIG framework only considers information gain criteria and requires an excessive computation burden. Second, the BIG framework can support one goal-oriented case, but not yet the change goal-oriented case. In this respect, we propose a new BIG framework named BIGexplore. BIGexplore has two main features compared to the previous BIG framework. First, it can provide a more sequential next view to the user. Second, BIGexplore can more properly update the prior even if the user changed their intended target. In other words, it can support the changing goal-oriented situation. The searching scenario in BIGexplore is designed with three assumptions to support a general information exploration. First, users have their intended target. Second, the users cannot know the specific location. Therefore, users are going to find their targets by repeating the scanning and refining actions in the information space. Based on the searching scenario, we designed the BIGexplore's interface. BIGexplore's information space are randomly distributed, and users can conduct four types of search action: zoom in, zoom out, panning, and click. Also, BIG framework requires user behavior modeling to update the prior values. For this, we consider 2 points: whether the intended target is in the current view, how many items are contained in the view. Based on these points, 6 user behavior cases were designed. The searching scenario and the user behavior modeling are the base of the BIG framework. From now, 2 main algorithms of BIGexplore will be explained. The first one is the sequential algorithm. Sequential algorithm aims to provide a sequential next view with the maximum IG while continuous to the search action. Based on the user action, the algorithm makes the possible next views, then compare the IG values. Second, to properly update the prior during the changing goal-oriented situation, the initialize detect algorithm is proposed. This algorithm initializes the information space to a uniform distribution when the user does the changes search behavior 3 times. We conducted user experiment to validate the BIGexplore. Let me explain the experiment process and result. In the user experiment, we used 4 different frameworks to validate the impact of the 2 main algorithms and BIG update-based feedback in the information exploration process. Non-big is the framework without the next view provision, and big-bait is the base BIG framework. Semi-BIGexplore is with only sequential algorithm. We conducted 3 experiments. Each experiment has a different condition and task. The frameworks used in each experiment are also different. Experiment 1 is designed to validate the sequential algorithm in the one goal-oriented case. Non-big, big-base, and semi-BIGexplore frameworks were used in this experiment, and the task is finding one correct SIGCHI logo image among certain images. Next, experiment 2 is conducted to validate the initialize detect algorithm by comparing semi-BIGexplore and BIGexplore in the changing goal-oriented case. Participants are requested to find 5 facial images among the 200 images. Experiment 3 is different from experiment 2 in that the target images are unspecified. The task is selecting chair images that can fit nicely in an internet image. Because of this experiment setting, the user's searching behavior may differ from experiment 2. The experimental result can be summarized into 4 findings. Each finding will be explained in detail from the next slide. First, the sequential search algorithm could make better user satisfaction with low computational time. Task completion time is significantly decreased in the semi-BIGexplore. The right figure shows that big-based user experienced the stuck situation that the framework consistently provides a fixed view regardless of the user's action. However, in semi-BIGexplore's log data, the user received the sequential next views. The second result is about the impact of the initialize detect algorithm. Max prior ratio is about how well the system predicts during the browsing next target, and target prediction rate is whether the framework imposes the max prior to the next target. As you can see in the table, BIGexplore with initialize detect algorithm shows a better prediction performance in the changing goal-oriented case. Third, participants were more satisfied with the big-based feedback than the non-big in the information exploration process. Without the next view feedback, participants conducted more search actions for doing the same task. In the in-depth interview, they also explained the difficulty of using non-big in each task. As a final result, BIGexplore showed better performance on the information gain analysis. The big framework's essential is the lowering of uncertainty through the interactions. BIGexplore's information gain graph shows the user's target changing patterns by initializing the information space. The conclusion of this study can be summarized as 3 points. First, a significant decrease in the computational cost enables the retrieval process by the user in a large information space. Second, BIGexplore with the initialize detect algorithm detects the changes in the user's intended target and initializes the prior for an appropriate probability update. Third, the feedback of BIGexplore helps the user avoid unnecessary comments in the information explosion process and reduces the user's mental load. However, there are 2 limitations in our study. First, BIGexplore's user behavior modeling should consider the information similarity data to provide the next view composed of similar items. Second, hyperparameters of the 2 main algorithms should be further studied to more interactively detect the initialization point. If future study could deal with these limitations, we expect the BIGexplore can be implemented into the various information exploration systems.